The matching problem is one of the three problems that we were introduced to at the beginning of this topic of HMMs. So what exactly is matching? We are given a sequence of outputs all the way up to the final time step, uppercase T. And our goal is to find the most probable state sequence S star, which is argmax of S given V, the output sequence. So in other words, the output sequence is given, entire output sequence, all the way from 1 to T, and the goal is to find out the most probable state sequence that the hidden Markov model would have gone through in order to generate V. Because there's so many ways V can be generated. So which of the state sequences is most probable? And that we denote as S star. When we were looking at the forward algorithm, we saw the variable alpha, which was defined as alpha Ti equals probability of the output sequence until time step T and the probability that the state at time T equals Si. That's alpha Ti, and so it's a joint probability, and note the colored green. Likewise, beta Ti is the probability of the future output sequence T plus 1 to uppercase T given, this is given St equals Si. So that's the conditional probability. Now I will be constantly referring to T, lowercase t, as the current time step, and anything before T, time step T, will be referred to as the past, and anything after T shall be referred to as the future. So alpha Ti is the joint probability of past and present output and the state at the current time being equal to Si. Beta Ti is the probability of the future output sequence being generated given the current state is Si. So notice the difference. One is a joint probability and the other one is a conditional probability. Let's look at what their product will be. From Bayes' rule, probability of A, C times the probability of B given C equals probability of A, B, C. And in our case, the event C is St equals Si, which is marked in blue. In both cases, it's blue, and in the variable alpha, it's a joint probability, and in beta, it's the conditional probability. It's the condition. And the past output sequence, including the present, is A, and the future output sequence is B. And so alpha Ti beta Ti is given by this expression. Comparing it with the Bayes rule, C is, again, St equals Si. B is the future output sequence, and A is the past and present output sequence. Now, past output sequence and present output sequence is this in green, and future output sequence is in purple. Now, this accounts for the entire output sequence, v1 through v lowercase t, vt plus 1 through v uppercase t, and that's the entire output sequence, v, bold v. Let's define gamma as follows. So we saw what alpha ti and beta ti were, and we saw that alpha ti times beta ti is the probability of the entire output sequence and st equals si. Therefore, if we sum it over all si's, we get probability of v. Let's take the ratio alpha ti beta ti over summation alpha ti beta ti. That's equal to, the numerator has probability of output v and st equals si, and the denominator has probability of v. So the ratio gamma ti is the probability of the state at time t being equal to si given the output sequence v. So we just saw that gamma is defined as gamma ti equals probability of at time step t, the current state being si, and given the output sequence v, all the way from the initial output to uppercase t the entire time. So gamma ti can be computed for each time step t and each state I using the forward and backward algorithms, because it's basically dependent on alpha and beta. Now, since gamma ti is the probability of st being si at current time step t, the state being si, so we can simply take the argmax of gamma ti to get which was the most probable state at the time step t. And let's denote it by S prime t. Now what we are looking for is the most probable state sequence, S star. Can we obtain S prime t for each time step t? Let's obtain S prime t. So we get the most probable state at time step 1, the most probable state at time step 2, up to the most probable state at time step t. And if we concatenate them, is S star equal to this string S prime 1 until S prime t, the sequence of most likely states at each time step? Is that the most probable state sequence S star? The answer is no. This little example will illustrate the point that if we concatenate for each time step the most likely state at that time step t, we do not get the most likely sequence of states. So in this example, we have a HMM with 3 states, A, B, and C, and the initial state probabilities are 0.3, 0.3, and 0.4. The transition probabilities are shown by arrows. Now, what's the most likely or most probable state at time step 1? Obviously, it's equal to the state which has the highest initial probability, and that's C. So S prime 1 is C, because pi of C is 0.4, which is more than pi of A and pi of B, which are 0.3 each. Now, at the next time step, what's S prime 2? That can clearly be seen to be equal to state B, because state B in time step 2 can be reached in two ways. With a probability of 0.3, if the initial state is A, then it always jumps to state B in the next time step. So that's this pi A P A B. Otherwise, if the starting state is B at time step 1, which has a probability of 0.3, then with a probability of 0.9, it stays in the same state B at the next time step 2. And that's pi B PBB, which is given by, if you plug in the numbers, it's 0.57. And obviously, S prime 2 has to be equal to this B here, because 0.57 has to be the highest probability. The probabilities of state at time step 2 being A and C put together have to be 1 minus 0.57, which is 0.43. So obviously 0.57 is the highest. So S prime 2 is B. And we've already seen that S prime 1 is C. But if we concatenate S prime 1 and S prime 2, do we get CB? Obviously not, because from state C, there is no arrow to state B. So from state C, you cannot jump to state B. Although the most probable initial state was C and the most probable state at time step 2 was B, S star cannot be equal to CB because there is no transition from C to B. In general, S star is not equal to S prime 1, S prime 2 until S prime T. Therefore, we cannot use alphas and betas to find gamma and then find S star, the most likely sequence of states. We cannot use gamma T because we just saw that S star is not equal to S prime 1, S prime 2 until S prime T. So for this, we need the Viterbi algorithm. The end.